right, we're going to take another pass at our survey winners. Fingers crossed here. Go back to the top of the list. Do we have Chris Spears from Internet 2 in the room? Chris Spears, all right. We've got an iPad mini for you, I believe, at the registration desk. All right, we actually got one this time. Thank you. We're running a little bit early. Coming up next, we have Richard Steenbergen.
So, I'm Richard Steenbergen with GTT. You might formerly know me from InLayer. I got bought a year ago and now GTT. So I'm here to talk about MPLS RSVP-TE using Auto-Bandwidth, some of the practical lessons that we've learned from using it and where it makes sense and where it doesn't make sense in your network. So, quick recap of what we're talking about, MPLS Traffic Engineering 101. In a classic network with just IGPs, all you would have is a network path defined by the SPF calculation, whatever the lowest cost is by adding up a bunch of metrics. And that's fine for simple networks, but gets really, really complicated really quickly when you have very complex topology, and it's very hard to load balance. So traffic engineering takes this and adds an additional constraint. For example, find the lowest cost path that also has available bandwidth. And if you can't find available bandwidth, then maybe you would rather map the traffic on something that is 1 millisecond higher latency, but won't drop the packets. So to do this, the common protocol is RSVP-TE. And the way that it works is it goes out, it measures the amount of bandwidth between two devices on a network, going over an LSP. It makes a reservation. It tracks what circuit that bandwidth is going over. And it will deny additional reservations if you run out of capacity. And then hopefully you'll be able to find a path that actually does have capacity, the goal being to be able to manage your network without dropping packets, even when you've got large complex topologies with lots of different available paths. And the bandwidth is measured at the LSP, the label switch path label. So for every LSP that's configured, you have a bandwidth number associated with it, and then RSVP maps that across the individual links. So here's a quick example of where that would kind of make sense. Take a really simple network, and you say, how might I route from Los Angeles to Chicago? So that might be your shortest path to go up through Salt Lake City and then come over to Chicago. That might be your second best path, and that might only be 1 or 2 milliseconds higher. That might be your third best path. That might actually only be 3 milliseconds higher. That might be your fourth best path. There's lots of different ways that you can go about getting traffic somewhere. And again, the goal would be it's better to get the traffic there even if the latency is slightly higher than it is to drop the packet. So the real question then becomes, how do you go about measuring your LSP bandwidth? How do you figure out how much bandwidth you're going to reserve for a particular LSP? Because after all, you're talking about completely dynamic packet switch networks, and bandwidth can change in an instant. So how do you go about this? There's two main methods. The number one method is offline calculation. So this is kind of how the big carriers started when they first started doing this. They would have a bunch of offline tools that they would apply a bunch of fancy math to make a prediction. They would say, well, we kind of think the bandwidth is going to be X between these two devices for the next day. And you put lots of math and lots of external tools into that. And you can kind of get somewhere with it, but it's very fixed. It's the kind of thing you can only roll out every 12 hours or every 24 hours or even less often. But that was how MPLS RSVP-TE was first deployed. And the next method is Auto-Bandwidth. And basically this is having the router itself measure the traffic going across the LSP and dynamically update the reservation as the bandwidth changes. So that's what I'm talking about here. So the big advantage of doing offline calculation is you can use any modeling algorithm you want. You can get as fancy or as non-fancy as you want. You can pay someone a lot of money for a good solution. You can go hire a bunch of PhDs to come up with a very nice theoretical model. You can do whatever you want. But again, like I said, you are limited to how often you can go out and deploy, and you're also kind of you either have to spend a lot of money writing it yourself, or you have to pay someone a lot of money for software to do it. With Auto-Bandwidth, because it's run directly on the routers, you can respond to these rapidly changing traffic conditions. So if a link fails or if a peer changes and you now need to reroute traffic in 5 minutes, you can do that as opposed to waiting a day to adapt to those changes. So it turns out to be good at that. It's easier to implement, but you're kind of constrained to the algorithm that the router vendor gives you on your particular router. So here's kind of an example showing the bandwidth adjustment interval. So if you look at a 24-hour adjustment window, you're not being very efficient. If you look at a much shorter, so this example is like a 1.5-hour adjustment interval, you can see that you're being much more efficient. You're realizing the bandwidth is coming down at an off-peak hour, and you're now able to use that circuit for something else. So it's much better to do it that way. So next question is, how does Auto-Bandwidth actually work? It turns out, well, it's an entirely router-specific behavior, but it turns out that the two main vendors that do this, Cisco and Juniper, both implemented it in kind of the same way. Shockingly, a lot of similar employees going back and forth. So the algorithm kind of looks exactly the same. You have what's called a statistics interval. So that gives you one data sample. So for example, say you had a statistics interval of 60 seconds. You would, over a period of 60 seconds, measure the traffic rate over a particular LSP, and that would be one sample. You then have an adjust interval that looks at multiple samples and says, for example, say you did a 5-minute adjust interval. You would look at your 5 60-second samples, and you would say, at the peak sample that occurred during the last 5 minutes, was it a sufficient enough change for me to go re-signal? And if it was, then you would go tear down your old LSP, set up your new LSP, and preserve the new bandwidth across the network. Again, with the adjust threshold, that kind of lets you set how much you want to have change. So here's an example where Auto-Bandwidth works really well. You look at your 5-minute sample, or 10-minute sample, or whatever it is, and you say, well, the bandwidth changed, so now I make a reservation. Oh, the bandwidth changed again, so now I lower the reservation, and you still kind of mostly work. Here's an example where Auto-Bandwidth doesn't work well. If you have highly bursty traffic, you might get a burst that's very high. You might go increase your reservation right as you're falling down, and then later you might lower your reservation right as you're going up. So you want to have a quick time. You don't want to let it sit around for 6 hours and not react to changing traffic conditions, because you're always going to have changing traffic conditions. There's a feature called Underflow and Overflow that are used to have a default long adjust interval, but to react quickly in the event of a change. So say, for example, you might set a default adjust interval of 6 hours or an hour or something high, but then have overflow come along and look, and if it says there's been more than 5 samples that have been over X threshold that I wasn't expecting, I need to react quicker than I was expecting. I need to re-signal. And the underflow is the same thing, but in the opposite direction. So there's a lot of vendors that don't support underflow. It just recently got added in Junos. It's in iOS XR, but there's a lot of cases where it isn't there. So you've got to be careful that if you react quickly to an increase in traffic, you also need to react quickly to a decrease in traffic, or else you might reserve bandwidth that isn't really there. But what I'm really here to talk about is where it all goes wrong. So it turns out that RSVP-TE is very good at adapting to changing traffic conditions within your network. So for example, if you have a circuit fail and you need to find a different circuit within your network, it's great at that. It turns out to be very bad at adapting to changing traffic destinations. So consider that example from Los Angeles to Chicago. Say you're sending to a pier in Chicago and your pier goes down, and now you need to change the traffic to New York. For your entire next adjusted interval, you will not know that your traffic has changed significantly. You're not changing how the LSP is routed, you're changing which LSP the traffic goes on. That's where it tends to get problematic. So again, that's where you want to have very rapid reaction to make sure that you're not congesting your network. It turns out that overflow and underflow actually aren't all that useful. Basically, if you just consider, like I said, the previous example, if you don't have underflow, like a lot of devices don't, then you can't react quickly to decreasing traffic. And it also kind of doesn't really accomplish anything, because you could just as easily set your adjust interval lower and do the exact same thing. So at a certain point, there's really no point in doing it. You could just use a lower adjust interval, and that's probably the way that you want to go. The next big problem is, of course, the LSPs don't just create themselves. MPLS is not entirely automatic. It has a signaling protocol, but the signaling protocol still requires you to go configure an LSP every single time. So the big problem there is, of course, you've got to find some way to automate this. Usually some type of tool that you write yourself, or some type of third-party tool, or in some cases you have router vendors that have Automesh capabilities. And basically what this is you feed it a list of all your core links, and it will go build a full mesh of LSPs between them. The problem is it turns out to be very, very basic. So say, for example, Cisco iOS, you can create a list, you can create a mesh of LSPs from a template. The template turns out to be an access list. The type of access list that you can't remove a single entry from without nuking the entire entry. You have no capability to do multiple parallel LSPs. It's very, very simplistic. So in reality, you really need to have actual tools come along and create all these LSPs for you. Especially if you want to be able to manually change the configuration of an LSP later. You can't do it if it's created by most of the Automesh tools that are out there. Juniper doesn't even have a built-in Automesh. What they tell you to do is use commit scripts, which are a really handy tool for doing that type of thing, but that's kind of in the create-it-yourself category. The next big problem is large LSPs don't fit down small pipes. So remember, an LSP can only be moved as an atomic unit. You can't take an LSP and split it across two paths. You have to send it down one layer 2 path. So if you have one really large LSP relative to the size of the circuit that it's going across, you end up with a packing problem, an efficiency problem. So say, for example, you have 3 6-gig LSPs going across 2 10-gig circuits. What's going to happen is 18 gigs trying to go down 20 gigs of pipe. It should fit, right? It doesn't if they're running as 2 independent 10-gig circuits. You'll be able to fit 2 of them on one. The third won't be able to use it because you can't put 2 6-gig LSPs on a 10-gig circuit. So common workarounds for this. Number one, you could just go configure LACP bundles, so that makes your bigger layer 2 bundles. But the problem there is, again, you're constrained to the smallest path in your network. So say, for example, you had an OC48 still floating around your network. You could never route an LSP that is bigger than 2.5 gigs across it, so you need to go keep your LSP smaller than that. Common solution for that is to create multiple parallel LSPs. So instead of the 3 6-gig LSPs, say you just created 3 parallel LSPs for each one. Now you've got 9 2-gig LSPs, and that's going to pack much more efficiently. But again, you've got to go create all these LSPs and be responsible for this. Next interesting problem is how Auto-Bandwidth behaves under stress. So, for example, consider what happens when you can't find any bandwidth anywhere in your network, whether it's a real capacity problem or whether it's just a software bug that mismeasures. What is the behavior that you think you should do when you go to update an LSP and you don't have enough bandwidth anywhere to fulfill the need? One solution is to just leave the bandwidth signaled what it was previously, which might be a good thing or might not be a good thing, because if you previously signaled 1 gig and now you're trying to push 5 gigs, you're pushing 5 gigs across an LSP that's not accounting for it anywhere in the system. And if you leave that going, you're just going to sit there and congest your links and not know about it. One of the other behaviors that can happen is the LSP will simply fail to re-signal and will time out and go away. So consider the pathological condition where you've got a large number of parallel links. Say you've got 8 parallel LSPs going between 2 routers, and for some reason you run out of available bandwidth and you can't signal one and it shuts down. So now you've got 7. All the traffic that was eSyncing across 8 links now moves to 7. The traffic goes up for each one. Now you're more and more likely to not be able to get a reservation for that next one. It fails. You go down to 6. Boom, 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 all the way down to one giant LSP that won't fit anywhere. And you sometimes have to have a human come along and clear it out to restore things. So one of the things that we've played with is to try and create a more intelligent Automesh script. So imagine that you could create an Automesh script that lets you fork an LSP when it gets too big. So if you set a random threshold in your network and you said, I don't want any LSP to go above 1 gig or 5 gigs or 10 gigs, whatever it is. When you see traffic get to a certain point, you now need to fork. You basically want to create two parallel LSPs, split the traffic across them, and load balance. Turns out there's a lot of gotchas in doing something like this. So the first one is the newly created LSP is going to come up and signal with a bandwidth of 0 for your first adjust interval. So what's going to happen is if, in a good case, you have one LSP, you split into two, they both go over the same link, and so the one LSP is accounting for the traffic of both, and it kind of works out. In a bad case, you signal a new LSP, and it goes over a link that a different link. So now you've got over here, you're over-reserving on one link and you're under-reserving on another. You're creating congestion. And there's really no way in any of the current Cisco Juniper implementations to override this. There's not a initial bandwidth setting, so you can't compensate for something like this with an external tool. And like I said, it can lead to the whole pathological LSP collapse scenario. The next interesting thing is that Auto-Bandwidth really doesn't know anything about congestion. It's a simple counter. It counts the number of octets going across an LSP and derives a rate, but it doesn't know when the link is actually congested. So imagine, for example, that there's any type of bug or issue that causes congestion on a link that you don't know about. Your TCP is going to throttle back, your IP traffic is going to go down, and Auto-Bandwidth is going to adapt to that new rate. So you can get into a situation where if you don't have enough headroom in the way that you run things, you don't know about this, and you just sit there persistently dropping traffic and never reacting to it. You also have to be careful about what routers can actually see in terms of layer 2 overhead. So for example, we run an all Juniper network, and it turns out that the Juniper MT and MX series can't actually measure layer 2 overhead. So if you get a 28-byte UDP packet that's actually consuming 84 bytes across the wire by the time you figure in your padding, your frame overhead, and all that, you don't know about it. You don't know about even the headers, let alone any of the link overhead. So you might have a DOS attack come in, and you might have a 10 gig link sitting at 7 gigs that RSVP thinks is perfectly fine, but you're actually congesting the link and dropping packets. So basically, the practical suggestions that I've come up with for doing Auto-Bandwidth, I still think that it's ultimately a really good system. You can't really design a complex network that's modeling traffic every 24 hours. You can, but you'll be very, very inefficient about it, and you'll be spending a lot of money adding more capacity than you really need. So it's something you really want to try and use, and anyone that's running a large MPLS network that isn't using Auto-Bandwidth, I would suggest you really look at it, but be aware that there's a bunch of implementation details out there. So again, you still have to have humans monitoring it to make sure you're not getting into the pathological LSP collapse. You have to keep an eye out for all the different types of conditions that I talked about. My personal recommendation is don't bother with overflow or underflow, especially if you don't have underflow, but just use a lower adjust interval. But be very, very aware of vendor bugs. So for example, we've actually seen a lot of instances recently with Juniper where they have mismeasurement problems, which is kind of comical when your LSP measures at 50 terabits, and you're like, I'm not going to find bandwidth for that anywhere in the network, so it's just going to fail the signal. It's a little less comical when it accidentally measures 50 gigabits on an LSP that's actually not doing anything, especially when it turns out to be a very high priority LSP that comes along and preempts a bunch of other traffic and really screws your customers. So you really, really, really got to be careful for those types of measurement bugs. And we've seen maybe 6 different bugs over the last few years, including some that just recently were in the stable 10.4 extended life branch. So you really, really, really got to be careful that you're going to have this type of issue no matter what, whether it's your third-party tool or whether it's the vendor-provided tool, but you've got to make sure that your bandwidth measurements are accurate or it's not going to work very well. And like I said, careful monitoring of your network is still needed. And what I really suggest people nag their vendors for is one of the major annoyances that I have is there's an adjust threshold that says if the bandwidth has changed by a percent amount. So you might say if the bandwidth has changed by 5%, then I want to resignal, otherwise I don't. And remember that because of the way RSVP is designed, there's no way to actually just say, I want to change the reservation from 1.1 gigs to 1.4 gigs. You actually have to signal a new LSP with make before break, tear down the old LSP. It's relatively complicated and uses a fair amount of resources on the router, especially if you've got thousands of these LSPs across your network that are all resignaling simultaneously. So, for example, if you change traffic from 500 kilobits to 550 kilobits, you probably don't care. But there's no, on Cisco or Juniper's implementation, there's no minimum threshold by bytes. It's only percent. So you see a 5% change, you're going to go resignal. Really, the vendors need to work on better LSP Automesh capabilities. Like I said, the tools that are out there right now, not the best, and they really don't handle anything more than a very simple network. So if you create a very simple Automesh, but then you decide that you need to add a second parallel LSP, or you decide you need to tweak the setting on one LSP, you can't do that. So some more tools would really be useful. If you're going to make any use of overflow, then you really need to have underflow as well, or you're setting yourself up for problems. One thing that I'd really like to see is kind of a way to automatically fork large LSPs of a certain size. And I've heard that Juniper is doing some work on this, but I'm not sure what version of code that's going to come out at. But if you go routinely over a certain LSP size, then what you might actually want is dynamic creation of LSPs, not something that you have to go configure in your device, but something that will go automatically fork and load balance the traffic. And when you do that, you get the capability to correctly resignal both LSPs simultaneously, put the correct bandwidth values in each one, do all of that type of stuff. So it would be very helpful. One thing that turns out to be slightly annoying about having a lot of different parallel LSPs to balance your traffic across is it kind of breaks your CLI. So if you look at a show route and you now see 16 different next hops for every entry because it's balancing across the 16 LSPs, that gets really annoying really quickly. So a way to kind of hide that, again, with dynamically created LSPs, that's something that you could do. The ability to set an initial bandwidth reservation. So if you do have a third-party tool or an in-house developed tool that wants to come along and fork an LSP, go create the second one, right now you have no way to signal the initial bandwidth. You have to set it at 0 and let it run a full adjust interval before it sorts itself out. So the ability to come along and fix that. And then probably an operational mode command. For example, in Juniper, where you have to go commit everything, it might not make sense for you to have to go do a commit, and if you've got a very complex config with a lot of scripts, a very long commit potentially, for you to go change an LSP size. So like an operational mode command where you could go request an LSP size to change to a specific value. And then you could have third-party tools come along and keep an eye on the LSPs and reset them away from the automatically configured one if something like that came up. These are the things that I'd really love to see vendors implement. So far, no luck, but questions? Mike.
Still thinking I'm in grade school. James from Wide Open West. Have you tried anything from an automation point of view with creating new LSPs and then initiating like an auto-bandwidth, I guess, re-signaling, or like there's a command to do that, so.
There's a command in Juniper for certain to recalculate, but it doesn't actually do what you're thinking. There's no way for it to manually adapt to a new bandwidth setting. So we've done some stuff with this. We've done some commit script-based creation of LSPs, and so I can have a tool that comes along and forks LSPs as needed, and I can have dynamic bandwidth configured, or dynamic numbers of LSPs configured. But you run into the problems that I was talking about. There's no way to set the initial bandwidth. There's no clean way to certainly without a long commit to go readjust those types of things, and there's no way to even manually adjust it but then have it fall back to auto after some period of time. So those are the big gotchas with doing it.
Joseph with NTT. I've got a question about priorities. Did you have to use that very often to get around problems, or did you have to play with that at all?
So we do LSP priorities just because we have different levels of service we want to offer customers. So kind of our design philosophy was, instead of going out and buying a dark fiber system and putting all your eggs in one basket, to kind of go out and buy a bunch of lit waves. And one of the benefits of that is it gives you a lot of different diverse fiber paths. So for example, between New York and Ashburn, I've got 5 different diverse fiber paths. Some of them are going to have lower latencies than others. So if I have a very latency sensitive financial customer that wants the best path, I'm going to put them in a higher priority LSP that's going to go preempt some best effort traffic, put it on a higher latency link. So we make extensive use of it from that perspective. One of the other things that we had to do just to make things be sensible was give, so we have 4 priorities, and then we break each priority into 1 or 2 if it's a long LSP or a short LSP. So for example, I would rather have the traffic go slightly out of its way for the short LSP. So you take a circuit that might be 5 milliseconds and make it 10 milliseconds, rather than have it go to 40 milliseconds just so that a 75 millisecond path doesn't go to 80. So there's some manual optimization that you want to do on that front, but for the most part it kind of runs itself and does the customer prioritization that you would expect.
And the interval between recomputing, did you have to play with that a lot, or did it just, you pick something and you stuck with it?
We definitely did. We are doing 60-second samples and 5-minute adjust intervals, and there's definitely been a lot of cases over the years where that's caused problems. So an example, an early implementation detail was that the adjust intervals weren't all staggered. So if you had a 5-minute interval, they would all run at once, which would do bad things. So the way that it works now is that if you've got 1,000 LSPs, it'll do run every couple seconds kind of thing to spread the load. But so you do have to kind of look at that and make sure that your router resources are reasonable.
So there is a lot of slosh when it does that. Okay.
Yeah.
Thanks.
Any other questions? Thanks.
Thanks, Richard. Just a few notes. Coming up after lunch, we've got Brian Field from Comcast talking about topology discoveries using BGP link state, and Jeff Wheeler with Innovative Network Concepts talking about IPv6 neighbor discovery problems. We'll also have our first block of lightning talks. We still have openings for tomorrow's lightning talk block, so if you've got any ideas, please submit them. We're accepting submissions until 7 p.m. tonight. And please do complete the surveys. We're giving out iPad minis. We very much want your feedback on the program, the breaks, the meals, everything we got. We're going to go ahead and break for lunch a little bit early. We'll see you back here at 2:45. Thank you very much.